able to talk on any occasion, but especially to early career professionals. I'm going to be talking this evening about buried obstructions in the ground and also utilities and how those risks and hazards manifest themselves and how best to manage them. I personally feel from my experience that it's an area that in general we could probably do better at across the industry, and hopefully by the time I finish this evening you'll understand why I think that. I'm going to Gary's already mentioned the Menti. It's really two questions. I would like you to think about the hazards associated with buried obstructions in the ground and the hazards associated with buried utilities. And there's one question around hazards and another question around mitigations. I'm going to give a bit of context. I'm going to go through 3 case histories that will hopefully inspire and trigger thoughts in your brain around hazards and mitigations. But I don't believe I've got an exhaustive list, so I'm relying on a tremendous amount of insight from everybody on the call. So please, if you have got access to a browser on the side, go to menti.com, enter that code, and stick as many hazards as you can in the hazards question and as many mitigations as you can in the mitigation section, and we'll have a look at those a bit later on. The 2 pictures are from the case histories that I'll be talking about. The one on the left is very congested infrastructure, new and old, in the ground. The one on the right, a site investigation with very congested utilities. Yeah, so that's it. Good luck with the Menti. Just before the Second Gulf War, there was an awful lot of focus on intelligence, and Donald Rumsfeld, Secretary of State for Defense, was briefing the US government on the state of that intelligence, and he introduced this terminology around known knowns, things that we know. So in the context of tonight's talk, that might be a foundation in the ground from a building that's been demolished, for which we've got a really good as-built drawing, and we can see the outline of the footprint on the ground. So that would be a buried obstruction. We know it's there, and so that's known knowns. But we also have known unknowns. Very often service drawings are schematic. So we might know that there's a gas pipeline following a road, but we don't know where in the road it is. And they become our known unknowns. And then there's also unknowable unknowns, things that you just can't know are buried in the ground until you encounter them. One good example of that was a site investigation we did at the Port of Boston, where a borehole struck an electricity cable 6 meters below ground level. It wasn't on any drawings. It wasn't known to the operations team. It wasn't in any sensible sort of location for anything that you could have imagined, but there it was. And that's really residual risk, but it's also potentially very high risk. So those are the sort of 3 boxes, and hopefully you'll see that terminology unfold throughout the talk. The pink box is a box I'm quite passionate about, insofar as things that are knowable but unknown. The more effort you can put into moving things from that pink box to the yellow one by investigation, by really tenacious literature search and searching for records, the better for everybody. The earlier you can develop as complete a picture as possible, of what might be buried in the ground, whether it's demolished buildings, services, or whatever, the better for the project. And that's a real passion of mine. So a quick look at what the Eurocode says. As with most things in the Eurocode, it says everything and nothing. Doesn't refer to buried obstructions or services specifically, but in planning the design investigation, it says that we should provide enough information for adequate design of the temporary works. And so if you've got to manage during construction with buried obstructions, buried foundations or whatever, then that fairly squarely falls into that category. We've got to provide the information required to plan the method of construction. Same story. And we've got to be able to identify any difficulties that may arise during construction. All three of those squarely pointing towards our duty of care to have properly investigated and defined as far as reasonably possible things that are buried in the ground that aren't readily identifiable, known unknowns and unknowable unknowns. Design investigation shall identify in a reliable way the disposition and properties of all ground relevant to or affected by the proposed construction. Imagine working in a water treatment works where there's a buried tank in the ground, an old partially demolished tank, and part of your new structure is going to be on it, part of it isn't. You really need to know as early as possible where it is so that you can design around it. Presence of waste and man-made materials. Well, all buried obstructions and utilities are man-made materials, and the history of the site and its surroundings shall be taken into account. That's all good, but that's the design investigation, which comes in the Eurocode after the preliminary investigation. So which comes first, the chicken or the egg? Do you design your layout and then manage the risks that are in the ground, or do you investigate the risks that are in the ground and then design your layout? And there isn't a one-size-fits-all answer to that question. It's always complex, but hopefully you'll get some clarity on some approaches that we can take. So I think it's really important that for any site, as early as possible, you consider the complexity and the amount of experience or precedent that you've got for any aspect of the project, and specifically for what we're talking about, that's the complexity and precedent of the engineering that we're undertaking, the complexity and amount of precedent of working in a specific geology, and then for buried obstructions, the complexity and experience precedent of working in the Anthropocene, that is man-made problems. So the 3 case histories, 2 from Boston, 1 on the left bank of the quay, and I'll show you that in a second, 1 on the control room and 1 from a GIO water treatment works. For the left bank, our geology is relatively benign, our natural geology. And for a sheet pile wall, it's glacial till, for which there's plenty of experience and precedent as well. So down here, our geology is relatively benign. But we're interacting with a new quay wall with an existing quay wall. That means the engineering is very complex. And when I go through the site history, you'll see that the Anthropocene is also very complex in this red box. And really, we need to be doing as much as we can as early as possible in the project to allow the design concepts to fit around the dragons and monsters that may well be in the ground. The control room, the geology and the Anthropocene issues at much the same level, but this is a G+1 building on a raft foundation. The engineering is much more simple. For the ground investigation, actually the geology here is much more complex. The engineering is really quite complex. Excavations for tanks below ground level that themselves need piling, and piled foundations for structures through ground that may contain historic foundations and buried artifacts. The Anthropocene also in a similar place to Boston, very complex because there's so much buried in the ground, and relatively little available records of what's there. So we've done our best, but there may still be problems in the ground. And this kind of classification I find really helpful to have discussions with peers, our design teams, contractors and early contractor involvement, and discussions with client to make sure that everybody's in the right space for how nasty it might get when you start digging holes when there's stuff that we don't really want to be there. So back to the Eurocode. The definitions of the 3 geotechnical categories are okay, helpful, but not exhaustive. They don't really deal with buried obstructions in any explicit way. And so those matrices that I've just presented, I think are really helpful. You're never going to be in geotechnical category 1 if you've got congested utilities or buried obstructions. You will probably be in geotechnical category 2, but in certain circumstances, you may involve abnormal risks, exceptionally or unusual difficult ground conditions, probable instability. So there are instances where I think buried obstructions could carry you into category 3, but the majority of the time you'll be in category 2. Okay, so on to the case histories. Case histories 1 and 2, Boston. There's Boston in Lincolnshire on the Wash. A GA of the project. It's a flood defence scheme. So there's flood walls, new flood walls, sheet pile flood walls along the right bank of the river. A new barrier structure, enormous structure, 365-ton steel gate operated by 2 55-ton hydraulic rams. And then a new flood wall along the left bank, all of which is in the estate of the Port of Boston, which is well over 100 years old and has a checkered history in its development. Another set of gates and a new entrance into the port, and flood waters seal into an existing flood defence at Lord Foster Sluice. Geology, well, I mentioned it's relatively benign in the natural. We've got glacial till and alluvium in yellow and green. The grey is made ground, which is typically 5 to 10 meters thick, very, very heterogeneous, locally contaminated, and as you'll see in a second, stacks of stuff from the historical development of the port. In terms of site history, hand-drawn map from 1817, and the port is will be in this area, but in 1817 there were just 3 windmills there. By 1889, the port had been constructed. There's the dock and the dock entrance, but there isn't actually a quay wall along the left bank at this stage. It's just the river bank. There's some bathing stations and the Baths Reservoir along here, and a number of buildings around the dock and the dock railway, so some railheads in the dock. By 1905, most of those buildings have been either developed further or demolished and replaced. There's a new ship slipway coming down. Those are the main developments by 1905. Aerial photographs from 1930. Here you can see the slipway, and there's a slipway from the other side, and the dock and the railway. So our new wall is in this area here along the riverbank. By 1952, the left bank has been formalised with a concrete sheet pile quay wall, and this big sugar and grain silo has been constructed at that end. Things getting really quite complicated. By 1966, some more new buildings and railway along the new quay wall, and crane rails in along the new quay wall as well. So from the engineering department at the Port of Boston, we've got this standard detail, which shows a concrete anchorage, with anchor ties to a waning on the quay wall at the maximum bending moment, with bollard ties for the bollards that are intermittent along the top of the wall, but also passing reference to this alternative piled anchorage system, which is shown in dashed, with the anchor ties coming and tying onto this piled anchor trestle table. What you haven't got is a dimension, so you don't know where this anchor beam sits, and you don't know where this piled trestle table sits. So here's a potted composite history of all those historical maps, and we are building a new sheet pile wall in this area along here that will need an anchorage system somewhere back here. And actually not long after the start of the design and construct, this black area here was found on a new drawing that was unearthed. That is the anchor beam there and there from this standard detail, and these blue patches here are the trestle table anchorage of the existing quay wall. This was a real problem because the flood wall was proposed to be a sheet pile wall pretty much along this line, and obviously it's not possible to do a sheet pile wall through a big concrete anchor block, and so we had to come up with a different plan. So what I'm going to do now is dip into the BIM model of the job. Here's the river, right bank, left bank. Here's the barrier. This is the area that we're going to be looking at just in here, so that you can see how some of this congestion manifests itself. If I now drop this down so that you can see into the ground, you can see there's the anchor beam for the existing quay wall, and here's the existing quay wall. And if I zoom in a bit, there you can see the anchor ties and the bollard ties as well. We actually did a small trial excavation and unearthed this anchor beam in exactly the position that the drawings suggested it would be. This is a tunnel, a culvert from that grain silo to a crossing that used to take grain to the other side of the river. And the original plan would be a sheet pile wall in this area to use as the anchorage for the new quay wall, which is here at the front. The changes and the discovery of the drawing that helped us lay all this out meant that we had to change our idea for the anchorage, and instead we went for discrete tube pile deadman anchors. This had 4 or 5 specific advantages. First one, we were able to put the tubes either side of this culvert. We were able to put the tubes to the rear side of the anchor beam. We had a degree of X and Y flexibility in the position of the piles, which you wouldn't have if you had a continuous sheet pile wall. So if at any location a pile just wouldn't go into the ground, we could just step it back a meter and try again. That in turn meant that actually we could pre-probe every pile position and drive the piles, knowing that we could get them in. We actually, the contractor drove a pair of sheet piles with a vibro hammer to prove clear driving at each one of these locations before the steel tubes went in. We could also then use the steel tube as a temporary shoring to allow man entry to connect the anchors into the tube. We could connect at a high level so our anchors didn't clash with the anchor beam there. Lots and lots of advantages that meant that the risk of clashing with these existing entities was able to be designed out. And then if we just go a little bit further along, here you can see the piled trestle table. Oh, excuse me. There's the piled trestle table. And again, with the tube piles, we were able to design around that in plan and have the flexibility that we needed with respect to that. Okay. While I'm in the model, I'm going to skip on to the next case history, which is for the control building, which is highlighted in blue there. And what we'll do is we'll come in from, excuse me, we'll come in from the other side to start with. So there's the control room. I'll just cut it out. There we go. So the control room houses the critical infrastructure required for raising the barrier, the power supply, the hydraulic pumps. Oh, sorry, I didn't mean to do that. Okay, sorry about that. All the critical plant is inside there. Here's the flood wall. So the control room is actually on the defended side of the flood wall, but nonetheless, there are individual pedestrian gates and things within the flood wall. There's still a possibility that water may get to the wrong side of the flood wall and potentially flood the control room. And for that reason, within the works information, we were required to make the flood room waterproof. That meant bulkhead doors at ground level to be waterproof, which was small and narrow, which really constrained the M&E plant that we could get inside and how easy that plant would be to service. We needed a standby generator, which would have needed to be on the other side of those bulkhead doors, which was a real problem, which needed exhausting and refueling from above the flood defence, also a big problem. So the solution was relatively straightforward. You move all the critical infrastructure. Also, the other thing was in a flood condition, the building would become buoyant, so you needed hold down piles to stop it floating away. The solution, relatively straightforward. You put the critical infrastructure upstairs, all those problems go away. These are the MCC kiosks for the electrical. Here's the hydraulic oil supply, and the hydraulic pumps are in here. Here's the generator, which is now easy to refuel and exhaust outside on a platform. And all those design changes inside the building meant that we were able to consider the possibility of not using piles. So hopefully you got that orientation of where the control building is. Here's a plan showing the buried obstructions. In blue, the anchor beam. In pink at the front, old railway tracks and crane rails. Two historic silos here. A raft foundation from a previous building. Something infilled associated with the historic baths, coming partially underneath the building footprint, and also on here, but more difficult to see, are the buried utilities as well. So we took the opportunity to do a settlement load test. So we cast a small raft foundation, built up Kentledge using legato blocks and sand on 3 levels, installed a bunch of monitoring in there. And we were able to demonstrate through that monitoring that, in fact, we could use a raft foundation. That although there was a reasonable thickness of made ground, it was predominantly granular, and settlements would be immediate with no long-term risks of consolidation or creep. A view underneath of what it would like. Horror, 70 steel tube piles, clashes all over the place with anchor beams, anchor ties, existing utilities. Significant health and safety risks reduced associated with piling through those buried obstructions, associated with diverting buried services, and excavations required to exhume and potentially contaminated excavations to exhume bits of buried infrastructure. All the clashes designed out and the unknown buried risk reduced significantly in terms of sort of finance. There's obviously the capex saving from the piles and the piling, but also the risk of delay, critical delay. The control room, not surprisingly, is on the critical path for commissioning the barrier. On to the third case study. This is a wastewater treatment works. It's just a ground investigation. Just a ground investigation. Who knows? It's still quite easy to kill someone in a site investigation. We were doing boreholes. We'd done a services search and got services drawings. We'd laid the boreholes out around those services to avoid them. We'd had consultation with the ops team for anything that they knew from local knowledge. We'd done PAS 182 GPR clearance of the site. We'd done a surface CAT scan. We'd done a hand dug inspection pit, and we'd CAT scan the bottom of the inspection pit. What could possibly go wrong? The problem was that this was a change. This was borehole 1A. Yeah, I don't know whether it was borehole 1A, but we'd had to terminate a previous borehole, and we'd changed positions and we'd offset. There was perhaps elements of groupthink, that this was about the 10th A, B, or C borehole that we'd done where we'd have to offset. We went through a degree of process blindness. We'd gone through all the checks that I've just said and not detected anything. The problem was that there was a polyethylene pipe carrying raw sewage sludge from this wheel here to these pipes over there. And the thing that saved us was the experience, expertise, and competence of the driller, who immediately recognised the behaviour of his drilling rods was wrong, stopped work immediately, and that's why we had a near miss and not a very messy and smelly accident. Root cause? Well, we didn't, because it was a change. We moved on through the process without actually just pausing for that amount of time to take a step back and actually look and see these pipes the same colour crossing the area where we were. The big problem was that the pipes were polyethylene, so none of the techniques that we'd used detected them. That's a case history, a difficult and troublesome case history, where it felt like we'd done everything right, but what we hadn't done is just paused for breath, taken a step back, taken a good look round before we'd reposition the borehole. Here's a challenge. If we struggled to sink a borehole there, how is anyone going to build a piled foundation there? If you think those models that I just showed you at Boston were complex in the ground, it's going to be absolutely horrific for anyone that's got to build a new building in that area, and how you fairly and squarely share the risk between the client and the supplier for that risk is really challenging. And that leads me to this statement that came from a very wise, but will remain anonymous friend of mine. He says, a tender is an exercise in selecting the most ignorant, most desperate, or most commercially savvy supplier. And none of those things are good for a client, and none of those things, well, certainly ignorant or desperate, are not good for health and safety. And so really a baseline of what is or might be, might be known unknowns, or it might be good imagination of unknowable unknowns, what might be in the ground, built upon a complete a picture as possible, as early as possible in the project, is the best way to design out hazards, and designing them out is the best way to reduce risk. You do that early, and you apportion risk equitably so that everybody is working in the right environment, atmosphere, space to manage the ground risk appropriately. So mitigations, avoidance. I've given you some case histories now to hopefully help you understand the importance of concept design. Not saying, oh, it's just concept design. If it's concept design, that's when you've got the most opportunity to design out through avoidance of ground risk and utility risk. Of course, you need procedures, risk assessment and method statements, toolbox talks. Brief back is really helpful. So when you give a toolbox talks, you ask the operatives to brief back to you what you've said. A permit to dig system that's signed off before anyone digs in the ground. And if things change, then you stop and replan. Competence is important. You need experienced people with expertise and accreditations, CPCS cards and the like. But behaviours is probably the most important part of competence. So it's no good having poor quality RAMs and half-hearted toolbox talks and permits to dig signed off as part of a grudging approach to paperwork. Behaviours come from the top on site, but particularly from professionals on site, really have to set the bar high in the behaviours that we display so that others will follow those behaviours. That means really high quality RAMs. It means enthusiastic and committed toolbox talks. And it means really reinforcing this stop and replan rather than plow on because we've got to meet a deadline. Detection, yep, technology. I've mentioned most of these already. PAS 182 GPR clearance, cable avoidance tools, scans. You can actually get cable avoidance tool devices mounted on the arms of excavators these days, and you can consider some geophysics as well, but specifically to locate buried obstructions. But all of these are very dependent on operator competence, which and also generally have a degree of uncertainty still left in them. I mentioned at Boston we did probing, and that was very successful. And also we dug down and exhumed the anchor block, and those are opportunities that are available to you, but exhumation in particular. As soon as you start excavating in this ground, even trial pits, where you've got congested utilities, gets really, really challenging. So my conclusions: get the concept right, understand complexity and the amount of experience and precedent that's available for a site that's got buried obstructions and congested utilities. Know your known unknowns and investigate them in as much detail as you can. So this would have meant finding the anchor block at Boston a lot earlier than we actually did, for example. Do that as thoroughly and as early as possible. Literature search, record search. You need real tenacity in a desk study in this type of environment. Never accepting, oh, these are all the records we've got because we've lost them. Go to the public records office in Kew if you have to. Really challenge again on as-built drawings and available drawings. Go to the GEOLSOC library or the ICE library, get literature searches done by librarians. It's amazing what you can find in published papers. Detection by technology, probing and exhumation. Really important. Know how you'll build the works, including how you'll manage unknowable unknowns. And if possible, do that at the concept stage. Get contractors involved early so that part of the Eurocode, you provide the information to build the work safely, is covered off. And you can plan your investigations around that. Or you can say, well, we'll mitigate it at the construction stage, but understand what that means in terms of risk for buildability and design. Avoid this risk as far as you can through design. And if you can't, develop a baseline so that the risk can be shared equitably when you get into design and construct tender. I'm very nearly done. Here's an example of what this might look like. Here's a model of an old demolished surface reservoir with columns that used to support the roof and a base slab and walls and excavations for pipe work and what have you. This green slab is a proposed new foundation that goes in next to it. And you can see there at a glance all the clashes that are going to be encountered and what needs to be considered in terms of dealing with these buried obstructions before we put the new foundation in. That's what I mean by investigating early, thinking through the buildability and sharing risk equitably. Back to the conclusions, procedures and competence. One's no good without the other. And really competence is important, but it's those behaviors, those attitudes and that tone that comes from the professionals on site. So lead by example and challenge. And when you get change, stop, pause for breath. Don't horse on. Replan, but replan with clarity. Make sure you take a step back, zoom out, and reassess what might be there, not just what is thrown up through your process. So that's around about it. I like to put in a cheeky pitch. I've just set up a new YouTube channel. It's called Geology James. And this talk will be on there fairly soon, and I'll be getting up. This is one of my hobby horses, buried obstructions, but I've got dozens of hobby horses, and I'll be putting up similar sort of videos around a range of topics relating to engineering, geology, and ground engineering. So please, if you find the time, check that out on YouTube. Give us a subscribe and a like. I'd be greatly appreciated to help me get a bit of momentum behind the channel. So I'm done. We can open for questions, Gary, now, or should we have a look at the Mentimeter?
If we can have a look at the Mentimeter.
I appreciate I've run over a little bit. Right. Hazards. Whoa. How do you control Mentimeter? It's crazy. Historic foundations, damaging pre-existing measures, fire, explosions, contamination, UXO, Japanese knotwork cavities, mine workings, all fantastic stuff. Unexpected utilities, a stroke, health and safety, yeah, cutting off services and harm to people, brilliant. More utility strikes, basements, tunnels, pipes, sewers, cables, MOD, fantastic stuff. I don't know. I'm a bit of a novice with this. I do apologise. All sorts of fantastic things in there. So I'd say, yeah, time and cost delays. I mean, I've talked about that quite a lot. Danger to human health, damage to the environment. Yeah, I didn't pick up on that. That's a really good one. Tunnel, TBM diversion. All sorts of good stuff in here. I will find a way during Alejandro's talk to better consolidate these and have a look. How do I get onto the next slide? There we go. Mitigations. Don't think I've got any mitigations. Bit of a shame. I'll do a little bit of digging round on mitigations during Alejandro's talk, and if there's anything. Oh, proper desk study. Yes, please. I use the word tenacious. I don't think we're anywhere near tenacious enough for desk studies a lot of the time, and I don't think very often we appreciate how much we can do with desk study experience and expertise with old heads and contractors very early in a project to shape it. And the key question is always going to be, if we've got these hazards in the ground, should those hazards in the ground shape the project? should we change the project to avoid the risk in the ground, or is the project so constrained that we've got no alternative but to accept? Designing out is always the best way. Cool. I'm going to stop sharing, and should we take some questions, or is Alejandro ready?
Jim, Alejandro's ready, so if we can move on to his presentation and save the questions for the end, that'd be much appreciated. Thanks for stepping in.
No worries at all. Cheers.
Are you ready, Alejandro?
Yes, I am.
Excellent. Thank you.
Everyone see the presentation?
Yeah, that's fine.
Yeah, okay. If the internet is not working properly, please put that on the chat, and I try to stop. If hopefully it's gonna be working properly. Apologies for being late, guys. I'm Alejandro, Health and Safety Manager at Tadway Central. Today, I'm just gonna share with you a brief introduction about Tadway, the health and safety strategy that we are implemented in Tadway Central. I will explain the 3 case studies. Hopefully, they're going to be relevant to you guys, geologists, and I will conclude with some examples of what to expect on a construction site. So as you're aware, guys, probably some of you are not, but a Tadway is a project that is improving the sewage system in London. So we're building a 25 kilometers tunnel by a 7.2 internal diameter, and the main purpose of this tunnel is to capture all the sewage water that is currently being discharged into the river. Why? Because the current sewage system in London was built, I believe, in the 19th century. So at that time, there were 1 million people living there, and Joseph Gazaget, he built this sewage system for 3 million. However, there is now about 9 million people living in London. So when it rains, the system doesn't cope with the capacity, and there is some overflow water being discharged into the river. So the purpose of Tadway is basically reducing the sewage discharge and hopefully having a less polluted river. So there is 3 different sections in Tadway, the Tadway scheme. I'm currently working in the central section. There is 2 companies in this section, Laing and Ferrovial Construction. And as part of Tadway Central, we have 9 different work sites locations across London and the heart of London, like for example, Victoria, which is next to Embankment Station, or Blackfriars, and so on. There is, as you can imagine, there is a variety of health and safety risks and hazards. And this is because there is a complexity of activities that we carry out in this project, like marine operations, tunneling, civil works, working in sewage, etc., that made the project complex and challenging, but also make it quite exciting to work in. And I'm just listing a list of the main health and safety risks that we have to deal on a day-to-day basis. Usually, we review the top risk for the sites on a monthly basis, based on the activities that we're gonna be undertaking in that period, and we try to make sure to have the right and adequate controls in place to manage the top risk associated with the activities that we carry out during that period. There is a health and safety strategy in Tadway Central, and it's based on 6 principles, the ones that you can see currently in the screen. I'm not gonna talk about all of them, otherwise we probably don't finish the presentation. But we're strong believers in Tadway Central of the power that leadership, bespoke processes and procedures, communication, collaboration, and engagement have in the creation of an excellent safety culture on site. And these factors are and have been a key in the successful delivery of the project. So far, we haven't had any significant accidents in Tadway Central, and we haven't had any fatalities. And touch wood, we're not going to have any significant accidents in the project. However, we do have accidents as any other construction site. For example, in the picture that you can see at the top, I think that's associated with it's not as good as a gym, a presentation. I don't have that model with me, but it's very important. And I think now in construction, we're starting to use more BIM to help with the understanding of the hazards. So that model that you see on the right-hand side, that was carried out during the design stage, and that was for the internal structures that we are currently building in Albert, which is a site near Vauxhall Station. So in the planning stage, based on these BIM models, we actually identified the best systems for undertaking working at high activities. And then after these hazard identifications and implementation of the controls, same as Jim, it's very important to deliver good quality briefings and toolbox tools to the workers. And I think by using BIM models is a good way of helping them with the understanding and identification and perception of the risk that they have to deal on a day-to-day basis. In Tadway as well, Tadway Central, we put a strong focus on engagement and communication. And we do different activities to engage people on site to get their recommendations, suggestions, but also it's important to give feedback on a day-to-day basis to their suggestions, as this helps us to improve our standards. And I think so far we're doing this very well. There is a good engagement and communication in the project, and all of this is supported by a strong commitment from project directors, project managers, and in general, the management team that they are engaging and they're going on site, they talk to people, and this helps to improve the standards in Tadway Central. So now, guys, as I say, hopefully these case studies are going to be interesting. The first case study, it was some excavation challenges that we faced during the excavation of the shaft at Blackfriars. So during the excavation of the drop shaft at Blackfriars site, we were encountered with a significant challenge during the last 5 meters. This was a 51 meters depth shaft, and there was a potential for the base of the shaft to fail if the dewatering system would have failed. So it was a significant challenge, but however, with a good planning and design out of the race, we could actually deal with the situation effectively. There was an independent review carried out by a team of geologists and different experts, where they qualitatively consider different mechanisms of the base failure in the shaft at Blackfriars. And one of the hypotheses. Can you hear me, guys?
Yeah, it's fine.
Yeah, okay. So there were various hypotheses that they consider. One of them was a hydraulic fracture. However, this was discounted because of a high horizontal stresses within the Thanet plaque. The other hypothesis that they consider was a bleed of the Thanet sand plaque due to a bleed forces water exceeding the applied weight. We had the dewatering system in and around, as you can see in this picture. So we have a dewatering system in and around the shaft to offset these uplift forces. However, as I said, if this dewatering system would have failed, then the consequences would have been really severe. This is the dewatering system that we actually have at the moment, the present time in Blackfriars. As I said, there was a dewatering system in and around the shaft to manage these forces in case that there was a failure of the base of the shaft in the tunnel sun. So the possible like negative consequences that were considered was that there was possibility of a soil disturbance directly below the shaft, and this may have extended a limited distance outside the footprint of the shaft, potentially affecting nearby buildings. The geologists, they say that they estimated that between 1 and 2 meters of excavated material could have a raise above the shaft level. And there was also probability, as you can see in the pictures, of displacement of the section of the tunnel immediately adjacent to the shaft. And also, as you can imagine, if this would have happened at Blackfriars, the consequences also would have been very costly and time consuming. We were told during that a review by the experts that we only had 2 hours and 35 minutes to implement a system if the dewatering system would have failed. So we implement based on that information and advice from this multidisciplinary team. We implement a action plan. This diagram here just briefly show what we implement. So we have a main power supplying power to the dewatering system. So if this main power would have failed, then we have a backup generator, and automatically there was a text message sent to the management team and to WJ, that was the company managing the dewatering on site. Then if the backup generator and the main power would have failed, then we have another alternative solution to prevent that disaster occurring in the shaft at Blackfriars. So we have we install an audible and a visual alarm on the shaft just to evacuate the people on site, and also we have some pumps to bring water directly from the River Thames to increase the restoring forces by filling the shaft with water. Luckily, we didn't have to get to this line. We already finished the excavation of the shaft at Blackfriars. We installed the base slab, which is 4 meters high, and thanks to the contingency plan, to the planning that was put onto this work, we deal with the situation in an effective way. And these are just some examples of the dewatering system and the live monitoring system online that the engineers were checking on a daily basis to ensure that the dewatering was working properly. The second case study, it was presence of a hypoxia ground. So in Cadway Central, during the excavation of the shaft at various sites and during the excavation of the main tunnel, there was a probability of encountering a hypoxic ground. And according to the geologists in the project, this hypoxic ground has been as a result of years of historical dewatering in the London Basin, resulting in a significant cone of depression in the lower aquifer, which in turn drained the strata above it, the Thanet Sand Formation and the Abnor Formation. I believe this left air pockets in the sand and gravel of the Abnor, which reacted with oxygen to produce nitrogen-rich gas. So from health and safety perspective, and putting this in simple words for us, this means that there was a risk of a deoxygenated ground in the shaft that potentially was going to deplete the oxygen in the atmosphere. So usually in Tadway Central, for the construction of the shaft and of the shaft and the tunnels, we work under the British standard PS 6164, and based on these standards, we just get all the guidelines and the main controls that we have to implement during the construction of the shaft and the tunnel. So the implications of encountering hypoxic ground, they were quite negative, and potentially they could have resulted in neurological disorders, headaches, dizziness, and potentially fatalities. So usually we needed to keep the oxygen levels between 99.5 and 23.5. So what do we do to implement an effective system in place? So we have, as you can see in the picture, in the right-hand side, we have to, obviously, we install ventilation, but we increase the volume of the ventilation in the shafts where there was a possibility of encountering hypoxic ground. We install a live monitoring gas monitors at the pit bottom. I think we have a Trolex system, and it's a system that is connected at pit bottom, and then at the top we have a screen where we can see the live readings of a different type of gases like hydrogen sulfide, carbon monoxide, oxygen, etc. Also, when we reach the level of the shaft where there was a possibility of encountering hypoxic ground, we ask everyone working in the shaft to carry portable gas monitors. We provide training and toolbox to the people working in the shaft, as well as to anyone visiting these areas. This picture that you can see where the excavator, Lynch excavator is, that was shared with us, and basically was shared to give the workforce an understanding of how the ground, like the color of the ground, was going to be during the excavation, where there was a possibility of encountering a hypoxic ground, and it's like a kind of a greenish ground. Also, we have permits to enter the shafts that they have to be issued and approved by a competent persons. In our case, it was the chief manager and the lead miners. And before we actually start any works inside the shaft, all of the chiefs, they have to issue a permit to enter the shaft to make sure that the ventilation is correct, the right levels of gases are correct, and that everything is in place to prevent any of these risks being materialized. In the ventilation system, because at this stage it was a very important item, we installed visible and audible alarms. So if this would have failed, the alarm would have activated, and everyone would need to evacuate the shaft straight away. It's a requirement in Tadway that everyone accessing the shaft and the tunnels we need to be trained on a tunneling safety training scheme and tunneling entry and emergency procedure. And in these trainings, people are taught about how to use, we call them MSAs, but they're self-contained breathing apparatus. The last case study is in relation to some difficulties that we face during the excavation of the connection tunnel at Victoria. This is a site near embankment station. So as you can see in the picture, that's the shaft that was approximately 49 meters depth. And towards the right, we built the connection tunnel that was connected to the main tunnel running under the River Thames. So What was the difficulty here? We have difficulties because the shotcrete was not adhering to the sand. So as you can see at yellow section, we were excavating and there was a sand channel. So the ground was very unstable. And for the shotcrete to adhere to the sand, it was quite difficult. In the project, we do some meetings, some multidisciplinary site meeting that we call required excavation and support sheets, where the sequence of the excavation is discussed and the methods to apply toolbox talks based on the ground conditions and the ground profile, they are discussed as well. So in our case, we were advised to install 3 meters for pulling boards or sheet piles and follow an excavation every 1 meter. So these 4 sheet piles over 3 meters long, and we have to excavate 1 meter shotcrete based on, you can see actually an example at the top showing the colors in the phase of the excavation. So that's an example of the sequence of the excavation that we have to follow. And luckily for us, it was successful. It was very time consuming, as you can imagine, because every 3 meters we have to install these 4 piles, and it proved to be very difficult at the beginning for the shotcrete to adhere to the sand. But this shows the importance of having a good multidisciplinary team on site, and always putting a safety at first. And I think consequently this help directly and indirectly to improve all the other aspects in construction. And I think this is the last section of the presentation. I put some pictures of examples of some incidents that I have experienced in the project. First example, I think I never thought that I was going to experience a fire on a construction site. It's very unlikely to have a fire on a construction site. Usually, I think the probability is very, very low. And even the London Fire Brigade, when they were on site, they say to us that that's very unlikely. But anyway, it happened. We have a compressor that was housed in a metal container, and we believe that one of the lithium batteries that we use for power hand tools, that was at the cause of the fire. The fire didn't spread to other locations because it was actually contained in the metal container. So it was a localized fire. It didn't spread anywhere else. But as you can imagine, the consequences and the time investigating the accident, property damage, there is some cost involved in these accidents. So I think you can see some bullet points of the reality in a construction site from health safety, from me as a health safety manager in Tadway. So usually the activities and the method assignments that we plan, they're not always executed as they're planned. And this is because I think construction is a fast changing environment. And today we're doing an activity, and tomorrow is you go on site and you find a totally different site, maybe different people, because there are lots of subcontractors. So the management of change is a challenge, and it's very difficult at some times. And I think right now is for personnel is one of the most important aspects to prevent and to reduce accidents on site, because when people don't plan the activities properly, that's when we have usually accidents on site. Adaptability is key to quickly respond to difficult challenges. I think, as mentioned it before, but you will never work on a construction site where accidents don't occur. There's always accidents happening on site. I believe that fatalities, they can be eliminated. You can work on a construction site without any fatalities, and I believe that. But we're always going to have incidents, and that's why it's important the reporting of near misses, getting feedback and recommendation, giving feedback to the workforce, and getting the recommendations and suggestions. Getting on site, speaking to people, because this is one of the most effective ways to actually identify opportunities for improvement. One important thing as well, usually in health and safety, we spend our efforts on investigating accidents, and obviously that's important because we need to learn from the accidents. But I believe that most of the time, 99% of the time, people and the teams, they do everything well, following the standards. And this is the things that we need to highlight and we need to investigate. We need to carry out positive investigations. We need to identify what we're doing well. And we need to share lessons learned about this between not only Tideway Central, but between the whole construction industry to improve the sharing of lessons learned, and at the same time reducing accidents, significant accidents and fatalities in the construction industry. These are some references, guys, that you can. The first one, that's a quite interesting research by Tim Newman. He's a geologist. He did some work on Tideway Central in relation to hypoxia ground. I think that that research is actually free. You can download that from the Imperial website. And that's it from me. Thank you guys for listening. Hopefully this was an interesting presentation with relevant case studies. And if you have any questions, please put them in the chat, or you can actually send me an email or contact me if you would like to get further information about anything else.
Thank you, Alejandro, and thank you, Jim. Some really interesting points have been brought up today, especially the importance of teamwork between multidisciplinary teams on site on projects. Obviously, the importance of planning and visualizing hazards and risks is actually quite an important thing that's becoming more and more the norm. So we'd like to invite the audience to ask the speaker questions. Has anybody got any questions? Okay, I'll ask one then. So, Jim, where would you like to see the industry going in the next few years with buried services? What would you like to do that you can't do at the moment?
I think the thing that I don't like is this notion that you can transfer ground risk to the contractor and that you can kick the can down the road. As the complex gets bigger and more complicated, that picture becomes bigger and more complicated. But for the most part, I really believe that the thing to do is what I was really hopefully came across from the talk, is do as much as you can as early as you can. It's incredible what you can do with a good desk study, a couple of vibrant minds, a good sketch, conceptual sketches. I don't know how many of you are on LinkedIn. Lee Taylor put a great post on there with a conceptual sketch of engineering geology in the Cotswolds. And those pictures really speak 1,000 words. The example I put up at the end of my slide with a geological model, the existing structure and the proposed works all integrated in 3D so you can spin them round. Involve people that wouldn't normally be involved at that stage of the project in discussions. Doesn't have to be formal ECI, but have contractors involved so that you can talk through how you'll build the job before you fix the concept design. so that you're always maximizing that chance to do more before things are cast in stone. And if you can do that, then you have the chance to either design out or at least design something with buildability in mind, rather than getting to the wrong side of a contractual procurement boundary and then just having to deal with everything in the D&B contract, and you're on the back foot from the start. Your job then is to mitigate through options other than avoid, and that's substandard. We can do better than that, and we should do better than that. And I think BIM, Leapfrog, things that help people visualize, help broader groups of people. You know, you can involve the foreman with around a BIM model, to have discussions about how you'll build the works. It makes toolbox talks, you know, or inductions. It can make all those things more vibrant so that you can do what you, when you get to site, you can create a more vibrant and upbeat communication of the risks than, have you read the RAMs? Good, will you sign this, please? And so, you know, we've got all these tools at our disposal now, and I think it's about vibrant discussions at the start and on site around collateral that allows us to make our points much more clearly, and help people understand what's being asked of them much more clearly, is really the way forward. I don't think there's going to be huge advances in techniques to help you find buried obstructions in the ground. I don't think there's an unknown technology sitting out there waiting there that's magically going to find all the utilities exactly where they are. I think it is about managing that, and I think a lot of that is around attitude, leadership, and designing out. Huge onus on designers.
Okay, thanks, Jim. So let's take the first question. I think Tom Morgan was first. If you'd like to unmute yourself, Tom.
Hiya, thank you for the talk. I had a question for Jim, and it was really about, because you were saying about in the talk being tenacious, and as you were saying just now as well, about being as thorough as you can early on to prevent complications later on. And I was thinking about, say, sites where or projects where you're constrained by, say, time or budgets to really go as deep as you should in reality into it. Is there any way, have you got any advice for like an early careers member for kind of not challenging to kind of, but encouraging people to just give you a bit more time or a bit more budget allocations, just go a little bit deeper? What would you advise?
Sure, it's a fantastic question, Tom. I think those matrices that I put up at the start around complexity and experience and precedent, that had the sort of danger fields on them when you're right at the top of complexity, I think they're really helpful for communicating why we should be doing more. And heaven alone knows, I mean, we've got the engineering group on the call, the geologists. The ground, the geology itself can be hard enough sometimes, but nearly always once mankind has interacted with it, it gets really complicated really quickly. And it's being able to tell that story in a way that captures the attention of the attention deficit, or the attention poor people that are so busy concentrating on the money all the time that they haven't got time for somebody going, no, I just need more time to do a desk study. So use those matrices. That example I put up at the end of the visualization, where you can see at a stroke that it is actually going to be really quite complicated, and it takes a minute to digest why you ought to be trying to do more there.
So it's sort of concise visualization and communication.
Yeah, if you can do it on 2 slides, brilliant.
Okay, thank you.
Yeah. You're welcome.
Okay, I'd like to invite Mark Edmondson to ask the next question.
Hi, good evening both. Two fab presentations there. I've got a question for both of the presenters this evening. Jim, I think I'll pose yours first because I think yours is hopefully just a yes/no answer.
There's no such thing with me, you know that, Mark.
Well, all right, I'll challenge you to a yes/no answer, and it comes off the back of what you were just saying there, Jim.
Yeah.
Whereby it's about kicking the can down the road, and it increasingly in the sector of work I work within, we're imposed with amended contracts that hand the ground risk entirely over to the contractor, and it's from the employer. Is that reasonable?
So I'd point you to the slide in the presentation that says a tender. It might be slightly different in your case, Mark. I accept that, but in normal procurement, a tender is an exercise in employing the most ignorant, most desperate, or most commercially savvy supplier. So if your contractors are commercially savvy enough to be able to somehow generate change around the unknown and unknowable risks, that's good. If they can't do that, then they really need to be working out, are they too desperate for the work, or are they too ignorant of the risks that are in the ground? And if you can pass all three of those tests, then I think there's still money to be made. I would prefer a more equitable share of the risk. I don't believe contractors should be project funders. And how does a client get apples with apples tenders if somebody has massively underpriced risk in the ground?
Sure. Thanks, Jim. I think just as a rebuttal there, I think it is a worrying picture. Increasingly, you as a contractor are being asked to sign up to these sort of risk, but then presented with an inappropriate level of data to fully assess that risk. And you gave some great examples there where there were big risks involved to a contractor. It's very important that if there are gaps, they need to be filled if you're asking that contractor to sign up to that kind of contract. So if I move on to Alejandro, possibly a bit more of a technical question. In part of your presentation there, it's something that just leapt out at me. You gave a very precise figure of 2 hours and 35 minutes to react to a problem. I'd be very intrigued as to who has given such a very precise number to, you have, if your dewatering system for whatever reason fails, you have 2 hours and 35 minutes to react. What do you do? And I think I recall you said you would pump water from the river. Now
we were gonna sorry, go.
That to me is was there a plan in place to fully implement that risk? Because that struck me that that would require some phenomenal pumping.
Yeah, it was. I think we put a lot of work on the contingency plan, and I don't know actually who gave that exact number, 2 hours and 35 minutes. But based on that figure, we actually implement a system, and we have three different alternatives: main supply, backup generator, and then if the main supplier and the backup generator would have failed, then we were going to be ready to actually pump water from the River Thames to alleviate the forces of the base of the shaft to prevent that happening. So we have a system in place ready to actually pump water into the shaft. But I'm afraid I don't have the answer to your first question, Mark, in relation to who give that accurate number. to us. No idea.
Thanks, Alejandro.
Okay, so I think in terms of trying to keep us on time and on schedule, so everybody can have some dinner. If I just invite John Davis to do the last question, and then we'll close after that. So hopefully it's a short one.
Yeah, possibly not. Thank you. Thanks, guys. I was going to make two controversial statements, questions, and see if we could get a reaction from our speakers and from anybody else. The first one is really is for both of you, and the second one is probably more fairly just for Jim. So the first one is, most of you may be aware that Tideway, the client organisation, placed some very significant constraints on dewatering, and in particular, basically dewatering outside the coffer dams and outside their site hoarding lines. So the first statement, controversial statement is, did that make it, if we think about what Alejandro told us, did that make it a safer project? And the second controversial statement, which is really more for Jim and for anybody else if they're allowed to chip in, is I know Jim's got a bee in his bonnet about desk studies, and so do I. I don't think as a business we do them very well, as an as a profession we do them very well. So I propose that actually, given what normally happens in organisations where the desk study is given to the most junior staff to do, I would propose that it would be better for the more senior staff, with grey hair in my case and even less hair in Jim's case, to actually do the desk studies rather than passing it, because you need that breadth of experience, I think. So over to you guys.
Alejandro, do you want to go first? Did the constraints on dewatering help or hinder health and safety? Or would you prefer not to answer, given that you've got a client?
That's why I asked you, Jim, as well.
I think.
Yeah, I still might have a future client or not if I answer your question, John.
I think, John, I would prefer not to answer that question right now.
Fair enough. I think
it
it hindered you. I'll be upfront about it. I think it hindered you.
Yeah. In terms of desk studies, the answer isn't binary. It never is it? I do think that there's a big part of a desk study is scale work or business as usual work, getting an enviro check, and reporting all those things, getting the geological map, doing all those things, building the first stage of a integrated conceptual ground model, ideally as some kind of sketch linked to a risk register. And I don't think it would be appropriate for grey or bald or both to be doing all of that. I do think, though, that with experience you can get to those ground models really quite quickly. You can look at some historical maps and you might miss a few bits of detail, but you can get to the big picture really quite quickly. Softwares like Leapfrog and BIM in general allow you to integrate your ground model with what you're planning to build, with what you think might be in the ground. And so picture paints 1,000 words, whether it's a hand sketch cartoon with a load of arrows on it that links to a risk register, whether it's something more tangible like a Leapfrog model. I think getting that picture up front and a risk register that might have 100 lines in it, but that you filter to 5 that you take to really present to the client to say these are the things that really matter. So we're talking specifically today about berries obstructions. Now, if there is an unexpected obstruction in this part of the site and we discover it at construction, that will mean 12 months critical delay. Okay, that gets the attention of your client. And there's no way that you can reasonably expect early career professionals to be able to get to that kind of conclusion quickly and easily. So there's two elements to it. There's one is drawing up the business as usual ground models. There's the senior input to help combine that together, to sense check it, to make sure there's nothing missing, to go through the risk register, really filter out the cream to the top, and then find a way to write an executive summary. And an executive summary is another thing in geotechnical reports I don't think we do particularly well. We don't really understand executives, and we don't really understand summary. It's about turning what's in the report into bottom line for the project. What do these risks mean for the project? Is it months of critical delay? Is it millions of extra pounds? And I think that's the way to go. Pictures for those that are short of attention, bullet point executive summaries that really get to the root of what it means for the project.
Okay, I think let's finish it there, because there might be some tummies rumbling now, I think. But I'd like to say thank you on behalf of EGS and the ECG BGA to both Alejandro and Jim for putting together two excellent presentations and taking the time out today. And thank you very much. Cheers.
Thank you, guys.
Okay, I'm going to finish the recording now and.
Gary?
Yeah.
I'm going to send you a link to an FTP. Could you put the recording on there, please?
I will do. I've got to shoot off, so I'll do it tomorrow. If that's okay.
No problem. Yep.
I've got a rugby match in 15 minutes.
Good luck. Play well.
Yeah, we won't talk about risk there.
Cheers.
See you guys. Good luck, Jim, with the YouTube channel.
Hey, thank you.
Yeah.